The last part of my talk, I want to just give you a little bit more of a perspective on our disruptive technology and the progress we have made at Solexel. So how do we make our cells? We actually start with a reusable template. This is a P-type silicon wafer, and no really special quality requirements, because this is really a harvesting ground for growing our thin cells and processing our thin cells, and we do that many times over a template. Next step, we actually form a porous silicon layer on the surface. It's really a surface modification process with you create nanopores. We have a controlled porosity profile over the wafer. This porous silicon actually serves has two important functions. One is it's an excellent epitaxial seed layer, and also it's an excellent release layer when we are ready to do the liftoff. So the next step, we grow our silicon, thin silicon, using atmospheric pressure epitaxy. And this is in situ doped. We actually program the doping in situ. And then while the thin silicon is on the template, we finish. Remember, we have back contact, back junction cell architecture. So our backside of the cell is exposed. We finish all of the backside processing, which is really most of the process steps. And at that stage, we are ready to lift off. But to do the liftoff, so far we have processed the cell on a very robust template, so thin silicon is not compromised in terms of yield. Then we use a very inexpensive polymeric sheet. It's a 100 micron sheet that is laminated on the cell, process cell. And then we define the release boundary with laser, and it's simply a lift-off release. So by the way, this is the world's largest area liftoff, and we do that we do that instantaneously on demand. So the important thing about this liftoff process is make sure that you can lift off on demand and not prematurely as you do the process. And we have essentially mastered that with our manufacturing technology and process. So basically, after we lift off the cell, the sunny side is exposed. So there are a couple of steps which involves the texture and passivation. We do the proprietary passivation. Remember, for high efficiency, that passivation is extremely critical, the quality of that. And then we finish the final high conductivity cell metallization. So we don't use any silver. So this is very inexpensive metallization, and of course no metal on the front side. The template actually goes back for the next reuse cycle. We reuse it over 100 times. So far we have done it over 50 times. And then the cell with the backplane is a pliable cell, you know, and also the backplane enables us to integrate the electronics for enhanced energy yield. We have done that in our product. So basically that's the process flow that we have. I should mention that the cells we can package either in standard glass modules, or in very lightweight, flexible, semi-flexible cells. I have these single cell prototypes just to show you. You can pass around. This is actually what I have here is a these are live cells. So this is a 4-cell flex lightweight package. And in fact, it's alive. I have some LEDs too. Yeah. So anyhow, these are essentially about 5 watt. Each cell is a 5 watt cell, full square cell. Now, our technology, as you recall, the flow has two. So essentially, in our fab, all the tools are standard bleeding edge solar commercial tools. Two tools are unique to Solexel. One is porous silicon, and the other one is epitaxial silicon. Now, we have taken two proven processes from the semiconductor space, porous silicon and epitaxial silicon, and successfully mapped and scaled them to solar, working with our manufacturing equipment partners. So this is one of the unique tools. This is actually in our fab in Milpitas, our high-volume batch porous silicon tool. If you're familiar with porous silicon, really the tool that you can find is more of a R&D tool with one wafer type, one wafer at a time process. So what we have developed with our partner is the world's first, and to our knowledge, only high productivity batch porous silicon tool for solar. This tool provides throughput of about 640 wafers per hour. For our process, this is about 25 megawatt per tool per year. And we form porous silicon with very low chemical consumption and very low cost. Our cost is about 1.5 cents per watt with this porous silicon tool. And excellent porosity and thickness control over the entire template areas. And it's also important that this tool, because of the consistency and uniformity that it provides, it enables us to achieve very fast, high-yield mechanical release with extremely high yield. The other tool, which we call Supreme 288, this is our high-volume epitaxial tool. It has a highly modular architecture. This is, again, I believe, the world's highest productivity epi tool. It's an atmospheric pressure epi tool, modular architecture, 288 wafer batch size. For our technology, it provides about 440 wafers per hour, and this translates to about 18 gigawatts of cell production per tool. We achieve good uniformity and repeatability, very high deposition rates on the order of 2.5 microns per minute, and very high PCS utilization, very high quality of doped N-type silicon on porous silicon. So this is very important. We consistently get over 300 microseconds for our N-doped absorber that we deposit with this tool. And the tool provides in situ clean with HCl. So every 10 to 14 runs, we do one clean, in situ clean with HCl in the tool. This is an example of a cross-sectional profile that shows our template. This is a porous silicon, and this is our doped epi. So we actually, using our technology, we have achieved what is really a world record for thin crystalline silicon efficiency, large area efficiency. This is actually NREL certified efficiency of 20.1%. The cell area is 243 square centimeters, 156 format, full square. And again, as you see, of course, it's the cell itself. This is before packaging is pliable and flexible and planar. You know, the VOC is over 680 millivolts. This is actually larger than any front contact cell you see out there. We expect this to go in the near future over 700 millivolts. JSC over 38 and fill factor over 77%. So the cell power is 4.9 watts and short circuit current 9.25. So in fact, this landed us on this NREL's. I'm sure many of you have seen the NREL's best research cell efficiencies graph that they update regularly, and recently they have put Solexel here. And I should also mention a distinction that so this is for, they actually added this new category of thin film crystalline. And one distinction to remember is that for us, this is actually full area 243 commercial scale. Many of the cells that are represented here, not all, but many of them are lab scale, small area. So actually, shortly after we had submitted that for NREL measurement, we went to a higher champion. Typically, our cross-calibration with NREL is a couple of tenths of a percentage absolute. So we haven't yet done a new NREL certification. We see a very short-term roadmap to with our technology to 22% cell efficiency. For us, that would enable module efficiency of 20%. For this cell, really, you see that the cell power is 5 watts. I think, again, a record wattage for thin silicon cells. It's also interesting to look at the low light performance. Now, this is a champion. The mean efficiency in our line is 20% with a very tight distribution, actually around most recently about plus minus 0.4%. So if you take a cell from our mean efficiency bin, 20% at 1 sun, and then measure the efficiency at, for instance, 0.39, about 0.4 sun, we get, with the STC efficiency of 20%, we get reduced light efficiency at this, under this condition, over 19.3%. So this represents a pretty good low light performance that's important for energy yield of the panels. Because of excellent bulk lifetime, surface, which is greater than 300 microseconds in our technology, surface passivation below 10 centimeter per second, and also light trapping structure, we actually achieve pretty decent quantum efficiency. What you see here, this is the these are the internal and external quantum efficiency. This is IQE, this is EQE. The difference, or the difference being accounted for by primarily by the reflectance or optical reflection losses in our cells. Our weighted optical reflection loss is around 3%, 2.5%, 3%. So this represents a very good performance in our thin silicon cell in terms of quantum efficiency. We have also been climbing, in fact, this has been a very nice momentum, climbing the efficiency ladder with time, and also tightening our distribution in our line. This represents our current baseline flow with a mean efficiency around 20%, and then actually the latest distribution is around plus minus 0.4%. This is range, max mean range. So this is all for full area cells with 43 micron absorber thickness. So as I mentioned, another important parameter is normal operating cell temperature. This is it's important to, if you have a technology module that operates at lower temperature in the field, obviously that's better in terms of energy yield. So actually, we have done measurements in the field on our full-scale 60-cell panels over a 2-week period, compared side by side with standard crystalline silicon panels. In this case, thermocouples attached on the cell inside the panel and also behind the panel. And basically, the NOCT for our cells is about 5 to 7 degrees cooler than the reference crystalline silicon panels. We do have this is something we had projected in terms of reduced NOCT performance. We have also, again, as I mentioned, the cells, our cells, we can package both in standard glass modules and rigid modules and also flexible lightweight modules. To make the modules, we use standard back contact module assembly and testing equipment and using standard tools. We also leverage OEM scale through contract manufacturing of our panels. Our technology has embedded distributed shade management, so every cell has its own integrated bypass switch in case of shading. So that actually, that is the first stage of what we call smart modules. That actually, it is integrated, so I can't say exactly at what stage it's done, but it's fully integrated with the cell. So, and really the way we do it, only Solexel technology with the backplane enables that. You couldn't do that with the standard wafer-based cells. And also, as I mentioned, we are developing BIPV rooftop shingles with Owens Corning. We have done extensive reliability testing on our panels, and just to summarize that, what we have seen is excellent module reliability. Great thing is that it's crystalline silicon technology, no exotic material, and we haven't identified any issues with thermal cycling, damp heat, humidity freeze, and highly accelerated tests. Many of these actually had multiples of the IEC requirements. and another important test is so-called potential induced degradation, PID, and our panels don't show any PID effect. We are moving towards full module certification by middle of next year, so we don't see, based on the extensive reliability data we have to date, we don't see any roadblocks. Very quickly on the go-to-market strategy, our strategy is partnering with our strategic customers, we have already, on the production front, we have already demonstrated our technology on our pilot engineering line here in Milpitas. We are now working on proving the high volume manufacturability of our technology on the copy exact high volume tool set. And the plan is that we will ramp copy exact lines and we'll begin selling panels in 2014. Essentially, our technology enables us to achieve unsubsidized levelized cost of electricity in the range of 5 to 6 cents per kilowatt hour. That really represents grid parity in many regions. So both in terms of efficiency and cost, those are enablers for very low LCOE, which ultimately is the most important cost metric. Our modules, our technology actually appeal to all key segments of residential, commercial, utility scale, and specialty applications. We have signed up actually 8 strategic customers. These are top-tier global developers and distributors. And they actually are helping us to get to market by providing help and resources with testing, field testing, bankability, and marketing. So this brings me to the conclusion of my talk. First, let me leave you with some important takeaways. Really, for any PV technology and product, the most important metrics are efficiency, energy yield, and cost. And really, the most important cost metric is cost of electricity that you generate with your installed system. Crystalline silicon PV will retain its market dominance for foreseeable future. And there are a number of really important reasons for that. Higher efficiency at lower cost. Already definitely more competitive than leading thin film technologies. Proven material and field reliability track record. Nothing really beats silicon in terms of reliability track record. Well-established manufacturing infrastructure, both in semiconductor and solar space. Supply chain and manufacturing infrastructure is very well established and mature. It is a sustainable technology and material system. You can meet terawatt scale requirements without shortage of sand and silicon, and it is non-toxic. So these are very important. Highest performance crystalline silicon PV actually is based on back contact architecture, and that's what we do, followed by heterojunction emitter or HIT type architecture. And our technology, specific technology, which is kerfless thin silicon epi, actually enables combination of high performance and low cost because of the way we manufacture our cells. And this is done both through process flow innovations and cell architectural innovations, which really I haven't covered in this talk. And also excellent synergy between kerfless thin silicon epi and IBC architecture, which we fully utilize in our process. And in the case of Solexel, our disruptive technology, as I described, really has 4 major pillars. The combination of thin epi silicon and template reuse actually enables us to achieve very low costs, very low manufacturing costs. Combination of the innovative cell architecture, IBC architecture, the way we make it also, and the backplane technology enables high performance in terms of both efficiency and energy yield. And I showed you that we actually substantially reduce silicon consumption with our 43 micron epi cells. We make actually the world's largest back contact IBC cells with our full square cells. And template reuse is a very important enabler for this value proposition. We have done that over 50 reuses, and we see a clear roadmap to get over 100 reuses as we go forward. Today we have a champion, world record champion efficiency thin silicon, 20.6% full area, mean efficiency 20%, tight distribution, excellent reliability results to date. So very encouraging for as we move towards the commercial phase. And the combination of backplane and template actually enables us to always support silicon. So we have a very, very robust solution to the thin silicon handling and processing problem with our technology. And also the backplane technology enables us to make what we call smart cells. We have a lot of ideas along that, but already we have implemented distributed integrated shade management. So with that,